All right, we're about to pull back the curtain on something you see literally every single day, from the way a diamond sparkles to why a straw in a glass of water looks like it's broken. We're going to dive into the bending of light. But first, let's start with a cool little trick you can even try at home. Imagine you've got a coin at the bottom of an empty bowl. Now, you move your head back just far enough so the rim of the bowl completely hides the coin. It's gone, right? Okay, so what happens when you pour water into that bowl? Incredibly, the coin just reappears. So how is that possible? What's going on?
Well, as you've probably guessed, it's not actually magic. The answer is a really fundamental principle of physics, the bending of light. So, let's unpack this bent light trick, because it's pretty wild when you think about it. The coin didn't move an inch, your eyes didn't move, so something else must have changed the path that the light took to get from the coin to your eye.
And here's the core idea. You know, we're all taught that light travels in a straight line. But that's only kinda true. It only travels in a straight line as long as it's moving through the same consistent stuff, or what scientists call a medium. The moment that light ray crosses a boundary, say from water into air, it changes direction. It actually bends.
And this bending, this amazing change in direction, it has a scientific name. It's called refraction. So officially, refraction is just what happens when light, traveling at an angle, hits the border between two different transparent materials, like air and water, and changes its path. That's it. That is the entire secret behind our reappearing coin.
But why does light bend? What's actually causing this? Well, it all comes down to one simple thing: speed. Think of it like this. Air is like a nice, smooth running track. Water, on the other hand, is like a big patch of thick mud. You can sprint across the track, no problem, but the instant you hit that mud, you're gonna slow way down. Light does the exact same thing. We just call the track an optically rarer medium and the mud an optically denser one. And that sudden change in speed is what forces the light to change direction.
Now, to really see this in action, let's walk through a classic physics experiment. We're going to pass a single beam of light through a rectangular block of glass. This will let us map out the exact path the light takes as it bends.
Okay, first up, we have our ray of light. It's called the incident ray, just zipping along through the air. And you can see it's on a collision course with the surface of that glass. Now watch what happens. The moment the light enters the glass, it hits that denser medium, our mud, and it slows down. And here is the first crucial rule you've got to remember. When light slows down, it bends towards an imaginary line we call the normal. The normal is just a line drawn at a right angle to the surface. Think of it as our baseline for measuring the bend.
So now our light ray is traveling in a new straight line, but this time through the glass, until it gets all the way to the other side, and it's about to go through another change.
As it exits the glass and pops back out into the rarer air, it gets to speed back up. And this shows us the second rule perfectly. When light speeds up, it bends away from the normal. And check this out. The ray that comes out is perfectly parallel to the one that went in. It's just been shifted sideways a little. How cool is that? Okay, so we know that the change in speed is what causes the bend. But that leads to the next big question, right? How can we measure or even predict how much a given material will bend light? Well, we use something called the refractive index. You can just think of it as a material's light bending score. It's just a number. And the higher that number is, the more the material slows light down, and the more dramatically it's going to bend it. Simple as that. So let's look at the scoreboard for a few common materials. Air has a score of pretty much 1, which means it barely slows light down at all. Water comes in at 1.33, glass is a bit higher at 1.52, but then you get to diamond, 2.42. That is a seriously high score on the light bending scale, and this one little number is the key to one of the most beautiful things in nature. So what does that number mean? It means light travels nearly 2.5 times slower in a diamond than it does in empty space. This causes an extreme amount of bending. Light gets inside a diamond and just bounces and bends all over the place before it can escape. And that is exactly what gives a diamond its fiery, brilliant sparkle. You know, understanding this principle isn't just for explaining sparkly gems or little magic tricks. We've actually learned how to harness the power of refraction to literally change the way we see the world.
We do it by shaping glass into lenses to control exactly how that light bends. A convex lens, the kind that's thicker in the middle, focuses all the light rays to a single point. That's your magnifying glass or a camera lens. Then you have a concave lens, which is thinner in the middle. It does the opposite. It spreads the light rays out. These two simple shapes are the building blocks of everything from the eyeglasses some of us wear to the Hubble Space Telescope. So, from a simple coin in a bowl all the way to the most powerful telescopes exploring the cosmos, this bending of light is a fundamental force we've actually learned to master. It really makes you wonder, doesn't it? If we can already bend light to see the microscopic and the distant, what's the next frontier we're going to unlock by controlling its path?